Hello guys, welcome to a new video. In this opportunity, I want to talk about the simple pendulum. Let's do a quick definition of this. A simple pendulum is defined as a particle of mass m. We have a particle here of mass m that is suspended on this string, and this string has length L. If the particle, okay, this string is has negligible mass, so we don't take care about the mass of the string. Another thing is if the particle is pulled aside to position B, let's do something like we are pulling this particle to this position. Okay, the string is going to make an angle theta 0 with a vertical. Let's call this theta 0. It's already on the figure, but I just want to do an emphasis on it. And this is the vertical, as you can see. Initially, the particle we pull it aside to the position B, and when the particle is on the position B, it's making an angle theta 0 with the vertical, right? At this time, the string would be right here, represented by the dashed line. If we release the particle, the pendulum will oscillate between the position B and the position B prime. Okay? And it's going to be a symmetric motion between those 2 points. The particle is going to do this. It's going to move on this direction. It's going to do all this motion. Eventually, it's going to stop at this point B prime, and it's going to come back to the point B, and so on, over and over, going back and forth, and it's going to oscillate that way. To determine the oscillations, we must write the equation of motion, and we take into consideration that the particle is moving along an arc of this cycle. This is a cycle. This is a path. Is part of a circumference, right? The center of this circumference is the point O, right? We take into consideration also the forces that are acting on this particle. The forces acting on this particle are the weight of the mass, right, mg, and the tension of the string, we call the tension T. Let's play with it. We can see another forces or component of the weight on this problem. The components would be this, let's call Fn, like F normal, and let's call this one Ft, like F tangential. Okay? Well, let's write the equations to calculate the equation of motion of this problem. First, we say that the tangential force acting on the pendulum is equal to minus mg sine of theta, right? We see this angle theta here, okay? I will write the some lines inside the triangle. This triangle is a right triangle, right? This is the 90 degrees angle. Give me a second to do something faster. If we see this triangle right here, we can see that this is a right triangle, right? And this is the 90 degrees. This side would be the adjacent component, okay, of the triangle, and this side would be the opposite component, right? And obviously the mg vector would be the hypotenuse of the triangle. So this is the hypotenuse, this is the adjacent component, and this is the opposite component. As we know, the opposite component is the sine component of this angle, okay? So we know that mg, the hypotenuse, is equal to the, we know that sine of theta is equal to the opposite component dividing the hypotenuse. In this case would be the weight, okay? So we write that real fast. That way we have the tangential component of the force is equal to mg sine of theta. Well, where is coming this minus sign from? Where is coming from? Okay, the minus sign is because the force is opposed to the displacement. Whenever the particle is moving to the left, the tangential force is going to act to the right. And whenever the mass is moving to the right, the tangential force is going to act to the left. All the time, the tangential force is trying to stop the mass. That's why the minus sign. Okay, so we have that little equation. I will highlight it, and I will call it equation number 1. Okay, I will call it equation number 1. This is the second Newton law, the next equation, right? And we know that the second Newton law is equal to the mass multiplying acceleration. The particle is moving along the path where the tangential force is acting, so the acceleration is the tangential acceleration related with that force. This force is related with this acceleration. Okay, and this is the second Newton law, as you know, right? Second Newton's law, as you know. Let's call that equation number 2. Okay, I will call that equation number 2. I will highlight it, and let's do something else. Because the mass is moving along a cycle of length of radius L. Okay, let's see. I will use a different color, orange. Let's see this. Oh my gosh, I need a pen. So let's do something here. I have this path, right? This orange path. If we complete this path all the way around, we will have a cycle, a circumference, okay? And obviously the circumference will have radius L, okay? And that's the length of the string. Then the particle is moving, is doing like a circular motion along that path. as we know, the tangential acceleration of this particle, of this mass, would be related with the angular acceleration of the mass with this relationship. Tangential acceleration would be equal to angular acceleration multiplying the radius of the circumference, but the radius of the circumference is L. Okay? Because the mass is moving along a cycle of radius L. You remember that we can write this equation? You remember that the angular acceleration is the second derivative of the angular position with respect to time. Right? This is the second derivative of the angular position with respect to time. Okay, then we can write the tangential acceleration as we know is omega L, but omega is the second derivative of the angular position with respect to time. Then the tangential acceleration would be replacing this equation into this. We will have second derivative of the theta with respect to time multiplying the radius. Okay? But we know, let's see equation number 2. Force equal mass multiplying the acceleration, right? From equation number 2, we have that force, tangential force, is equal to the mass multiplying the tangential acceleration. Then, if we replace this into this, we will have that the tangential force is equal to the mass multiplying the tangential acceleration, L, second derivative of theta with respect to time. Okay? And we know that let's call this equation number 3. Okay? Let's highlight the equation. And let's see equation number 1. Equation number 1 says that force tangential is equal minus mg sine of theta. And equation number 3 is tangential force equal ml second derivative of theta with respect to time. We can make those two equations equal. We can equalize those two equations. Then equalization or making equal number 1 and number 3 equations equal, we have minus mg sine of theta equal to ml second derivative of theta with respect to time. Okay, guys, let's simplify this equation. The mass cancels each other because the mass is on both sides of the equation, and we will have something like this. Okay, let's do something. Let's send, this is minus sign here. We can send this side of this part of the equation, this term, to this side. Okay, and we will have something like ml second derivative of theta with respect to time plus g sine of theta equals 0. We send this L that is multiplying to divide on this part, or we divide by L all the terms of the equation, and this cancels with this out. Then we will have second derivative of theta with respect to time plus g dividing L sine of theta equals 0. For harmonic motion, when the motion is harmonic, the oscillations are small, and we can take into consideration that sine of theta is approximately theta when theta is very small. Okay, very small, for theta very small. The equation of motion finally will get something like this. It will look like this: second derivative of theta with respect to time plus g dividing L plus g dividing L equal multiplying theta equal to 0. Okay, this is the equation of motion. Let's call omega squared equal to g dividing L. Okay, to differentiate this omega from the omega that we used earlier, let's call it omega p for the pendulum. Okay, it has the same units as the previous one, but we want to do something a little bit different. Okay, if we do that, finally the equation will be written like this: second derivative of theta with respect to time plus omega squared theta equal to 0. And this is the equation of motion of a simple pendulum. Okay, this is the equation of motion of a simple pendulum which moves with simple harmonic motion, and this is the angular frequency of the pendulum. The angular frequency on the pendulum is equal to g dividing L. Okay, if we do analysis of the units, okay, we will have that the units on this, on gravity, is distance dividing time squared, and the units of the length is distance. Okay, and this distance and this distance, they cancel each other, and we will have the dimension analysis for this equation. Omega p squared, the dimensions are 1 dividing time squared. Okay, time squared. if we take root square on both sides, we do something like this, okay? Then the dimension analysis is going to show us that the angular frequency of the pendulum is going to have dimensions of 1 dividing time, okay? Usually we use seconds as unit of time. It will be something like this, 1 dividing second, okay? This is the frequency of the pendulum. Let's write it like this. G dividing L is the frequency, right? The angular frequency. But by definition, the period is 2p times dividing the angular frequency, okay? The period is the time that the mass takes to make a complete cycle in 2p times, okay? So then we will define the period as 2p dividing frequency, right? The period is the time that the mass takes to complete one oscillation in two peaks, in 2p periods of time, okay? And we can write it like this. T is equal to 2p equal dividing root square of G dividing L. We can write it like this. And now we can write the frequency, the normal frequency. The normal frequency would be 1 dividing the period. Is how many, the normal frequency is how many oscillations the pendulum makes in 1 second, okay? How many oscillations? And it would be written like this. Root square G dividing L dividing 2p. Okay, guys? Okay, guys, this is the consideration of the simple pendulum I wanted to talk about. Thank you for your attention, for being here in this video. Please comment if you want. You can subscribe to my channel, give me a thumb up, and share my content. See you on the next video. Bye.